everyone doing? Any questions? So I'm going to redraw the diagram that we were looking at last time. So we're looking at how polymorphism, polymorphic subtyping is implemented by having a model of this in C that corresponds to what the Java or C++ compiler and runtime system would do. And so in this example, there was two objects. A variable A that might point to an object of type A, class A. And if it does, the object, so the instance of class A, will have a pointer to the class object for A, for class A. So every time you say new A, you get an object, and that object points to another object that represents that class, the class A. So this is class A. And inside of this is, this will store the static variables, but the key thing we're focusing on is a jump table that has pointers to code. So that's, the first one is a pointer to the code that implements ping. There's two methods here, ping and pong. So that's for ping. And this one's for pong. And then this is the code for ping and pong. So we write it like this. And if you had this variable A that's pointing to a different object, we say new B instead of new A. Again, an object has a hidden instance variable named class. It points to a different class object. This is for class B. And it has a jump table. This class must implement pig and pong because it extends A. And it must have those in the same entries in the jump tables. You'll see in just a second why that is. So there's ping, there's pong. It also implements another method called with, so it extends the class. Ping is overridden, so there's a B implementation of ping. Pong is inherited, so that entry just points to A's implementation of pong. And then with, of course, is new. And last time we went through the details of how you model this in C. I'm going to show you a little bit of this today. We're not getting back into all those details. But to remind you, hopefully, what those key things are, I'm going to write here the names of the different structures that we find. So that there is a struct that gives the type of this thing. So the type of that thing is called struct A class. And that's a struct that lists the jump table. And that's static variable lists that. And there's a struct for this one called struct B class. And then there's also a global variable that is this thing. So that global variable is called A class table. So at any point in the program you want, you say A class table dot, and if you say A class table dot ping, you get that one dot pong. So this can be a little bit confusing. The relationship between this and that is that this is just the type. It's just the struct. It's not a variable. And this is a static allocation of a variable of that type. So that's the type of this.
Is that how C++ and Java actually implement?
Yeah. So this is how virtual functions work in C++, and this is basically how it works in Java. I mean, they don't use the same names, but this is how it works. Yeah. And the only thing that I'm leaving out of C++ is dual inheritance, multiple inheritance. I think it's perfectly fine to leave that out. So a function in C++, you can have virtual. They operate with polymorphism. You can't put them on virtual. They operate without polymorphism. So if you don't know, that's fine. It's not this cause. So just think of it as any function that operates in an object-oriented way. This is what we're describing. Okay. And then there's one other thing, which is there's a type that represents that. So the type of the objects themselves is struct A or struct B. So, you know, the type of this variable, the actual type is struct A, the actual type of this is struct B, but as you see in the slide up here, if you look at the function foo, the apparent type and the actual type can be different. And that's just exactly, you know, what happens in Java, as you know. But it's a little bit different the way that happens. So I can call that function foo like this. I can say new A. If I do that, then this, the A in the function foo point is like that. It points to one of those. Or I can say new B and construct an instance of B that also has width and the overrated version of A. And I'd have one of these. And then that's passed into foo. And you see that foo, the type of the parameter is void star. Why? No, I think you have it. Look at what's over here. The actual parameter can be two different types. Right? It could either be a struct A star or a struct B star. And in Java, how would we do this? Well, in Java, you would define foo like this. You'd say void foo A, and then you can say A dot K. And then when I call foo and I say new B, without the underscore, that's perfectly fine because in the class B I say class B extends A. So object-oriented languages have a notion of subtyping, and a subtype can always be substituted for the supertype. So that's why this works. I can have this variable A. Its actual type is defined as an A, but it can be a B, actually. C doesn't have this in the type system. So the only thing that we can do if we want a function that can take pointers of different types is to use the totally opaque pointer. They can take a pointer to anything. Now it can't just be anything. I could call foo with an int star, and everything would blow up. So it can't actually be anything. Where the same substitutability rules exist in our model here as exist in C++ and in Java. This must be, the actual parameter here must be a subtype in just the exact same notion of substitutability of struct A, but it's just not enforced in the language. So you just, as a programmer, you just better get it right. And to get we're sort of getting around the type system in the language is, so foo defines that to be a void star and uses the name A, B, to refer to A as a void. And then it has a local variable A that's of type struct A star. So A, like this, or like this, but the type of it is just this. So if we look at the call to this body, I construct a struct B. The parameter is of type struct B star. I have one of these. And then I call foo, it goes into a void star, and it comes back as a struct A star. The compiler has generated code that works if it's like this. Does that make sense? That's the apparent type. And the only reason that this is going to work at all is if anything that I substitute in looks exactly the same. It does everything that this does in exactly the same positions in memory. Because the compiler has generated code, thinking that, got A points to this. This is of type A class table star. Sorry, struct A class star. And I get here, and then pings in this position and pongs in this position. And it just generates the code for that, the static offsets to get there. And then, so long as you always pass in one of these, of course, that's exactly what you have. But if you pass in one of these, then when it gets to that point, and here's the call, right? So the call in here. So this is the Java version. The C version is like this, almost the same. I say A, arrow, and here's one difference. Class, arrow, ping. And the other difference is that, I'll come back to that in a second. If that A points to one of these, actually, then I come here and I get to here. And so now what is actually in memory is this, but the compiler generated code as if it was this. And that's why these two things have to be in the same spot. It's going to generate code for calling ping, and it's going to use some offset to get to it in the struct. That's just something in a struct. And now I'm given a different struct. And the key thing about this struct is the beginning part is exactly the same. So it pings in the same place and pongs in the same place. So as long as you do that, it all works. And you'll notice also that you can't call with. Even if I pass in a B, and there's a with pointer here, and if it was a B, I could call it. I could say A arrow class arrow with. You can't do that if the compiler generated code for struct A. Because struct A's don't have it. And that's exactly the way it is in Java too. I mean, if you in this case, the apparent type is A, the only things you can say here are things that are defined in the parent type. It doesn't matter what's in the actual. Questions about that? Is that clear or is it confusing?
So like in the diagram we're finding,
Yep.
the first A is the pointer pointing to struct A.
Yeah.
The triangle is the jump table.
That's the class. Okay.
And
They
then,
can paste it.
and then the last one is where A
That's
is
the code.
that's where it's the object.
That's the code. Yeah.
So on that declaration, where you construct a pointer, that's what the term, that's what actually, because the void AB, that AB could be A or B, but then when you set the pointer to a pointer, that's what makes it a like this is the parent type. You can only call A regardless of if it's A or B.
Right. So let me repeat what you just said, is that the very first line of foo defines the apparent type of the variable A. In Java, we wouldn't have that line, we just do it right here. In C, we have to have a void and then do a cast, that's what that line is for. And that the apparent type defines what operations, what methods you can call on A. Ping and pong, that's it. That's all that's defined for an A. And if you pass in anything else that isn't an A, it just better have ping and pong in the right place. But they could have different values here, which is what allows, this is the substitutability, gives us this polymorphic dispatch. That's what we want, right? We want this code that just was compiled as if it had this, but now I can pass it something else and it'll execute a different version of ping if I do that. Okay. So the other thing that's different, so it's different, the syntax here is A.ping, that's Java, I say A arrow, class arrow, right? So that's different. And then the other thing that's different is this A, and that's the value of this parameter that it's implicit in object-oriented methods, that there's a local variable called this, a parameter called this. We have to make that explicit. So that's why, previous slide, there's a this in ping and this in pong. Questions about that? Okay, so I'm going to show you another example in just a second, but let's take this now all the way to the conclusion of getting to assembly code. So this call, A arrow class arrow ping, is implemented by an indirect jump. And in this case, the address that I want to jump to is stored in memory. It's right here, or right here, right? It's at a certain offset from the pointer to the class. And so what we've done, and this is common to do, but it's not necessary, is to define a new instruction. It's called the double indirect jump, and it's like this. So jump star, and then an offset, in this case for ping at 0, and then the pointer to the class. So if R0 is pointing here, if R0 is the value of that thing in the class, then that instruction will jump to this code. But if A points here, it'll jump to this code. Same instruction, but where it jumps to is determined by the value of R0. Now that is exactly the same as two instructions that we already have. So you could also do this, load 0, R0, and then jump with an indirect jump to R1. So what the double indirect jump does is combine with load. So the indirect jump, the address you jump to is in a register. Right? And I can get it into a register by loading. What that does is loads that value into R1. Then I jump to it. Just like the return did. But because this kind of thing is very common, like every method call in Java and C++ is like this, it's common to have a double indirect jump. Instructions specifically designed for this. Now, before this is a GPC. Now that's a 2-byte instruction. So it would look like this, GPC 2, R6. Or to put it there. So looking at that, so that's different than the static call that we had previously would be something like this, jump, and GPC. Looking at those two things and comparing them, discuss with each other for just a second. What are the trade-offs? What's the benefit of this compared to that? And are there any advantages of this compared to that? Static versus dynamic. So what's the advantage of the dynamic jump? Yeah, it can jump anywhere. This one instruction, the compiler compiles it once, and depending on what code comes before it, it can jump anywhere. And specifically with polymorphism, it can call any implementation of ping, just simply depending on which class R0 is pointing to. More flexible, right? Any advantage of this? Well, how many memory accesses are required to execute this? Well, 0 or 1 to get the instruction. How many for this? It's easy to see here. Same thing. 2, right? Because I've got to load the target address and then jump to it. So, this is jumping to an address. This address is in a register. This is jumping to an address. This address is in the instruction. So this and this are equivalent, although this is a little bit smaller, so it's a little bit better. But this is extra. And we saw this exact thing when we compared static arrays and dynamic arrays, or static structs and dynamic structs. With the dynamic thing, there's an extra load. And so this is slower. And in fact, you learn in 3.13 that it's a lot worse because of the way that the processor pipeline is constructed. When you have to jump to a location that you don't know where it is, it's really hard to avoid having multiple stalls in the processor as a result of doing that. That's not for us to talk about, but it's worth thinking about now, is that you pay a price for this flexibility. Every single function call, method call in Java, and all the virtual calls, which are probably most of them in C++, is like this. They're slower than that, but it's worth it. It's worth it because you can write code that this one piece of code is flexible, that it can execute functions based upon a parameter to the code. So you have code that's parameterized by the values that it operates on, and in some cases by the functions that it executes. And that's very important, very useful for code use. And
The final classes, like means the first one, and then Java.
if you have a final class, so final means you can't extend it. So if you have a final class that doesn't extend to anything else, then yeah, you might be able to revert to, and there are tricks. So that even in other cases, you can revert to a static Java sometimes. I don't want to talk about that. You'll learn about that in free time. You can talk to me after class. So there's some tricks, because it's a big cost, and so we want to avoid the cost when we can. Okay, so this is, the next slide is just showing you that instruction, the double indirect jump, and then finally the code. So this is jump to ping, jump to pong, offset 0 and offset 4. And this is the whole thing with the Gpsc and the arguments and all that stuff. Okay? Dynamic jump versus all this stuff we had with static jump. So we're sort of done with that, but I want to show you a different example. So the questions first of this. Okay, so this other example I posted to Piazza in code used in class. And so what I did was, who remembers integer set and integer list from 210? Who did 210? Who remembers integer set from 210? I remember it. Same thing in the other class. I don't know. So I thought this would, maybe it'll trigger your memory. I'm trying to show you a simple example of what we're talking about that you can relate to. This should help you with the assignment. In the assignment, you're going to have to do something more complex with the polymorphic model that we built. Okay, so this is Java. An integer list is a list of integers. The details don't matter here, but the operations do. So you can add things to the list. You can check to see whether the list contains a number, and you can get the length of the list. This list, unlike the one you did in 210, is bounded. So it has a fixed size. The size is determined by the constructor. Integer set extends an integer list, and it changes the list so that integer sets don't store duplicates. So it has to override the add method, and the add method first checks to see if the list already contains the value, and if it doesn't, it doesn't add it. If it does, then it calls super add so that it can execute the add of the parent class, which is integer list. Everybody is with me on this, right? Now you get it. Is it familiar at all to anybody now? So, like this whole part of the room is you're not just talking. All right. Here's main. So I have a loop. This loop is accessing a variable whose apparent type is integer list. The first iteration through the loop, the actual type that it points to is an integer list. The second time is integer set. So I'm calling the code that you see add, and then the printf twice. Once with the actual type is integer list, the second time integer set. Both times the setter list are bound to size 2. On the first time through, it's an integer list, and I say add 1, add 1, add 2. What should the list contain?
1, 2.
No. 1 and 1. Right? And that's the first one, and that's the second one. Now the list is full, so it won't add 2. And so if I print, the print here, the label part will just print integer list divides 0 and integer set divides 1, so we know which one it is. And then it's going to print high length, I contains 1, I contains 2. So it should print 2, true, false. Right? Now if I run this again, but with an integer set, and I say add 1, add 2, what should I get? What should it contain? 1 and 2, because it won't add the second one, because that's a duplicate. So if I run it again with the set, it should say length 2 contains 1 true, contains 2 true. And you have this code, you have all this code that I'm talking about, so you can go run it and see that's actually what it does. That is the C version of the main that we're just looking at. It's basically the same, except it's a different language. And let's look at the specific differences. So the first specific difference is that I declare the apparent type of L not to be integer list, but struct integer list star, right? So it's like this, struct A star, struct integer list star. That's its apparent type. To construct an object, I run the new function, so it's not the new statement, it's new underscore, so new integer list or new integer set, looks pretty much the same. And then to call instance methods, I do this weird thing here, where I've got to add class and add with this parameter. So I say L arrow class add L, that's the list parameter, with this parameter, and then 1, add 2, and then print out the length, I class length L, I class, and contains 1 and contains 2. And that will do exactly the same thing. Questions?
I don't quite understand why we have arrow class in the middle. Like it's L arrow class arrow. I thought, because it's a bunch of usually references straight to.
So what I have is a pointer to an object, and I need to get to a method. So I have to use the class parameter of the object. So I've got A, it points to an object. Now this object contains all the instance variables plus an extra instance variable called class that points to the class. The class has the jump table. So to call add is defined in the class object. I've got a pointer to the instance. So I say, what is it? L, this is L, arrow class, arrow add. L, arrow class, arrow contains. Okay, so that explains this. And that, in fact, is exactly what's happening in C++ and in Java. It's just hidden from you in the syntax. Because if you think about it, you know that the methods are not defined in the instance. The instance just contains the instance variables. The methods are defined statically. And this is just making that very explicit. Right? The way to get to those static methods is to go through this dynamic format. Does that make sense? Thanks for the question. Does that make sense? Okay. So let me just show you also the implementation of integer set. This contains a few things here that are extra, that part of the machinery of things. So the very top part, that struct, it's a variable declaration, so it's declining the variable integer set class table, right? That's this variable for the integer set. It's of type integer set class, which is defined elsewhere. You can go before. It provides values for the three things, the three methods that integer sets and integer lists implement. They implement the same methods. You'll see the first one is add, and that's the integer set version of add. Right? So that tells you that add has been overridden by integer sets. If we looked at integer list, you would see that's an integer list add. But contains and length are inherited. So those are pointing just like here with Palm inheriting here. They're pointing back to the integer list implementations of contains and length. So that's the first part. The second part, so this does something we didn't talk about in class, which is it distinguishes public, private, and protected. You don't need to know that at all. You don't need to do it in the assignment. But it actually helps a little bit when you try to think about the different, sort of where things should be defined. So this it's just this. It's defining the structure of an instance. And it includes the public stuff, which is just class. That's the only thing that's public, the rest is private. And then everything else. So an instance of an integer set and an integer list have 4 instance variables: the class, the size, the length, and data, which is a pointer to an array of integers. So that's the second. That defines a type. The last 2 things are the 2 methods that are unique to integer sets. So the first one is add, right? So this is the one we're overriding. And you'll see that add takes a this pointer, which is void star, casts it to a pointer to one of these objects with the private thing added. And then does what we did before. It says, well, if this does not contain v, then add it. But the call that contains is done in this way. And then the add, that in Java is super.add. And this shows you how you handle super. And you'll need to do this in the assignment. I'm not going to say anything about it, but you need to, as you read the code, think through it and make sure that makes sense. And then finally, there's a constructor. So what it does is malloc something that's of size of that struct, initializes the class pointer to point to the class for that, the class object for that class, and then calls constructor function for its parent. If you look at the Java code, it's called super. Okay, so questions? So this should be pretty easy to read. So I recommend you take some time when you're getting ready to work on this part. The second half of the assignment is this stuff. So before you tackle that, download this, compile it, you can make it, run it, look at what's happening, and then take a challenge yourself to change it in some way. You might do what you did in Zoo 10, is to implement a set, so extend set, so that it does something that lists don't, for example, union or intersection. Or you might extend set to have, like you could have integer set logging, that every time you add would print something. Or you could add a remove method to both lists and sets. Okay, so do one simple change to this, and that will show you all the, hopefully, if you make it simple enough, you'll be able to extend this and have it work, and you can see where all the changes have to be. And I think this will help a lot before you start on the assignment, because the assignment's a bit hard. And you can always refer back to this as a template when you're doing things with this. Okay, questions? Okay, so the reason we did all of this was so that we can understand how object-oriented languages implement substitution. And the key thing about this, as I said earlier, the key benefit, so I can write a piece of code, and somewhere in that code, I call a method, but the actual implementation that runs will change dynamically at execution time depending on a parameter to the function. Now that idea is crucial to be able to write robust, extensible code. But there's different ways of doing it. So the object-oriented way builds this into the type system. In C, it's quite common to do it with just straight up function pointers, and that's what we're going to look at now. I'll show you also the Java version of it. So this is quicksort. It sorts integers, arrays of integers. Here's the call to sort. So what you do is you pass in an array of integers and the size, and it changes that so that it's in order. It uses the function right above it is a helper function that calls itself recursively, and sort of most of the meat of this is in partition. So we're going to focus on partition. And see if we can make this now. So I have quicksort, it sorts integers, but I don't want to have to rewrite all quicksort every time I have a list of different kinds of things. A list of strings, a list of student objects, you know, a list of cats, I don't know, all kinds of different things. I'd like to be able to sort them with one piece of code. Does that make sense? This is the way it is in Java. I mean, there's just a sort. I'll show you the Java in just a second. And it's just written once. In fact, you would never see sort. Because it would just be in a library, and there'd be a sort there, and it doesn't matter what you want to sort, you can sort it. That code was written without having to know the types of the things that are being sorted. How, right? So let's take a look at this. This is a list of integers, and the goal here is to make it so that I change this code so that it will sort anything. So I want you to talk with each other and just go line by line and identify whether that line really needs to know what the type is and why. Do that. Okay, so the main thing that's happening here with elements of the array is just copying them from one location in the array to another location or into the pivot value variable that has to be the same type as elements of the array. So there's sort of, the pivot value is dependent, it's an int, and that is an int because elements of the array are ints. And all those assignments kind of depend upon the type, but actually they just depend upon the size. And so we looked at all those places, and I, int, and I change everything to be an opaque pointer. So now rather than sorting arrays of ints, I will sort arrays of pointers to something. And this is actually what Java does with polymorphism, is that you don't get polymorphism on the built-in types. You only get it on, so you don't get an int, you get an integer. And so what would really happen is if you wanted an array of integers, you're going to have an array of pointers. But also if I had an array of strings, right, 3 strings, it would look like that. Those are the same, right? You look at this, these are just pointers. Now these are, the type of this, each of these would be int stars, the type of each of these would be char stars. But the thing about int stars and char stars is they're the same thing. They're just numbers. They're just pointers. And so I can copy them back and forth to each other. And to do that syntactically in C, I have to make them all void stars. So the generic version of Quickstart says, okay, give me an array of pointers. I don't care what they point to. And I'll sort the array of pointers based upon what they point to. And so there's only one place in Quicksort that's actually type dependent, if we do it this way. And that's the comparison. The thing that's underlined here. Is that determining whether something should be ordered before or after something else depends upon the type. To determine that for integers, it'll be one thing. To determine it for strings, it'll be something else. And in fact, you might want to order integers in ascending or descending order, right? So it depends upon even little details about the type, right? So that needs to be a parameter, okay? So the void start thing, perfectly fine, no problem at all, but this is a problem. Now, how would you do this in Java? Well, yeah, so you know that all objects have an equals method, but here, that just determines equality. I actually have to do inequality here. Does anybody remember how this? Oh, yeah. Yeah, exactly, beautiful. So Java has an interface called comparable. And if I declare, so I am going to say, okay, I have a comparable integer that will sort integers in ascending order. So I define this type, okay, and implement the method compare to. And then the quicksort version, the C version, the Java version of quicksort doesn't use void stars. It's an array of comparables. Now, that's just an object that has that method. And so, when I get to the point where I need to compare, I'll invoke compare to on the array. But now we know that in Java, let's say it's, the integer thing, each of these is a pointer to an object. And if each of those objects has a class pointer, and inside the class pointer is a jump table, and in here is the code for compare. And if I have another array where this is a different type, it'll point to a different implementation of compare. So what happens in Java is when you pass in a value, like the elements of the array, what gets strung along with it is a function. By having that thing have a different type, by having a different implementation of the comparable, I get a different function. And it's built in with the data. And that's polymorphism. Now we don't have, so we can actually do all this with the stuff we were talking about a minute ago. Well, we're not going to do that. We're going to have a function pointer directly.
So if we wanted to sort like an array of abstract types, right, we would have to implement our own comparable.
Yeah, that's what you have to do. This is what you have to do in Java. Java, it doesn't have sorting. I mean, there's a built-in comparable integer, right? But the quick sort or anything that would do inequality comparisons, you would have to provide something that had the compare to method. There may be other ways to do it, but that's not the point here. The point is that we're going to do this in C by passing in the function directly as a function pointer. Okay? Because the void star doesn't carry with it, the implementation of the function comparison. So essentially all I'm going to do is I'm going to pass that function as an extra parameter. So this function has to have a signature, returns an int, and takes 2 void stars as a parameter, because it's a list of void stars. And when I get to this place where I compare, I'll just call that function. And now whatever function is provided as the parameter to sort, now will determine the order. So, I'm skipping over this for the moment. If I want to sort a list of integers, I first, so let's look at the box below. I first declare an array of pointers to the integers. So that's PA. So if you look at the far right-hand side, I've got PA and A. And I guess the numbers are 3, 8, and 1. 3, 8, 1. This is PA. And then I write a function that can compare void stars if the void stars are pointing to integers, and it compares them the way I want them to. So the signature has to be void star, but I know they're going to be int stars because I'm passing in an array of int stars, so I'll pass them both to int stars. And then I just dereference A and B to get their values. So if I say star A is less than star B, then I return -1, less than. If star A is equal to star B, I return 0, equal to. Otherwise, I return 1, greater than. And then you just call sort like this. I pass in the array. Now here I have the type. What's the type of PA? What's the type of this array? Int star star. It's an array of int stars. So it's int star star. I have to cast into a void star star. Explicitly. So that's the first step. This is the length, and that's the comparison function. Now, if I wanted to sort an array of strings, all I got to do is, here's the array of strings, so that's this thing. I write a function that compares strings. This element t is, we'll talk about next time, it's the void star, it's just void star. Type that void star. And this is the code that will compare two strings. Or